Okay, it's working. Yeah, okay. So, good afternoon. Welcome to this lecture on reinforcement learning. My name is Patrick, and I'm a PhD student in Niels's group. And it's my pleasure to talk about this topic today. So, reinforcement learning, I think everyone's heard the term. How can computers learn through trial and error to do smart things? This is how the field once started. And it started with this idea of just doing more of whatever proved successful in the past and to reinforce these actions. So that's the reason for the name. But nowadays, reinforcement learning is much more than just trial and error search. In the pictures, you see three examples of successful reinforcement learning, like a backgammon board where this program TDGAM has been trained on, then like a collection of Atari games. Also, a neural network has been trained here through a neural network to play them. Through reinforcement learning to play and succeed in these games. And the last picture is like representative of a bunch of robotics tasks. In this case, it's like an ant where you can control the legs, and the goal is like to make it move. And all of these tasks have some way of interacting with the environment. Like you do some actions, see what happens, do some other actions and see what happens then. And time is always involved in reinforcement learning problems, and that is what makes it very different from supervised machine learning. So why is the lecture on reinforcement learning today in this course with a focus on physics? So deep learning can not only be done with data, but also with simulators or governing equation. That's one thing the two fields have in common. Another thing would be like the multi-step character, like, as I said, like in reinforcement learning, time is always involved, and I believe you've also seen like plenty of examples in this course where you have like a fluid simulation and you like observe it over time and try to learn that. And the last thing to mention here is the Markov property. If you don't know yet what it is, that's no problem. We'll get to it later, but just so you have like a rough idea of where things are going today. And understanding these connections like between physics and reinforcement learning is sort of the goal of today's lecture. So the first half of this lecture is an introduction to the core principles of reinforcement learning. I'll start with the reinforcement learning framework, which is quite generic and probably partly at least the reason why people are excited about that. Then I'll be talking about values and value functions, which are like a true reinforcement learning concept, the first we are going to encounter, and then about reinforcement algorithms that can solve for values and for value functions. Part 2 later then will be like understanding a bit more why reinforcement learning needs different algorithms than supervised learning. And yeah, if there are any questions, just let me know. I'd be more than happy to explain. So let's start with the reinforcement learning framework. If you've ever looked into reinforcement learning before, then it's very likely that you've seen a figure like this one. It's a schematic drawing of what I already began to explain, this idea of interacting over time. This is what reinforcement learning is all about. So let's go through it. So we have an agent. The agent is the entity that learns and chooses actions. And it can also be called a controller, or like in a game context, can be called a player. And the actions that it outputs, they go to the environment. The environment outputs a reward and another state of the environment, a new state of the environment. And the rewards are the sort of feedback that tell you what is good and what is bad, sort of the data of reinforcement learning. And yeah, the environment outputs them, and other names for the environment, like depending on the context, can also be like a simulator, world, a system, or a game. And if we let this play out now for a while, what we get is like the sequences of states, actions, rewards, states, actions, rewards. The sequences are called episodes. And then we have policies. That's the rule that is followed by the agent to choose actions. So mathematically, it's a function. Input are states, outputs are actions, and it's usually denoted by a pi symbol. And the overall goal of the setup is like finding a policy that maximizes rewards. So this is the basic setup of reinforcement learning. Yeah, and let's talk a bit more about what these rewards can look like. So there are two types of rewards. First one are immediate rewards. What's special about them is that you basically observe them after every step. So in this example here, the AND again that's supposed to run, you would get a reward of +1 in every step where the AND doesn't fall over, and a reward of +d for the amount that you moved along the x-axis. And as you can imagine, like if you combine them, they encourage like a fast movement to the right. And so if you like fulfill like the reinforcement learning goal of maximizing rewards over time, it moves like you can see this, yeah, it will probably move in the way you can see it here in this little video. And then there's the second type of rewards, like the delayed rewards. Like for instance, if you want to learn to play chess, you only observe a reward at the very end of the game when you either win, lose, or the game ends in a draw. And as you can imagine, these delayed rewards are the main difficulty in reinforcement learning tasks. Because in that situation, it's very difficult, like if you have early actions, to like understand which of these actions are like the reasons for the later success in the game. So yeah, again, in summary, like the delayed rewards here are the main challenge which you're trying to solve with reinforcement learning. So how do physics tasks fit into this reinforcement learning framework? So maybe you've seen this before in this lecture, like a fluid control task, where you have like this yellow object that is swimming in a fluid, and you have these three gates at the top, and let's say you want to move it through the left gate, so that's the goal. Let's say the actions are like the fluid field only in the outer areas. You cannot control the inner part, only the outer part. And now you have to somehow like achieve that it moves through the left gate. And what you would like do in like classic control setup, in a classic control setup, you would define a loss that somehow measures if the object is close to the left gate. And what you now do in reinforcement learning, you just can use the negative of this loss. Because remember, in reinforcement learning, it's not about minimizing quantities, it's about maximizing the rewards. So it's basically just a convention, but one has to be consistent. And another task like, for instance, error correction of numerical solvers, I think has also been covered abundantly in this course, like where the actions like of the temporal trajectory could be like to are the state change that you apply in each step, and the reward would be based on the similarity to a reference trajectory. And one can also take this one step further, like when you so you need not compare individual predictions to formulate a loss, but you could instead also use statistically formulated losses or rewards where you average over trajectories. And yeah, this can be more appropriate on chaotic systems, but it depends on the circumstances. So as I mentioned before, associating the effects of early actions with later rewards is the main challenge. And the classical way how you would like try to do that would be a rollout. You would evolve the system all the way to the end and just see what happens. Like for a game, you would just play it out all the way to the end. And a reinforcement learning concept is like to train directly a function that outputs for every state the expected future rewards. And that thing is called a value function, or also sometimes a critic. You can think of it as sort of a computational shortcut. Instead of like doing like hundreds of environment steps to have an idea of like how good is it to be in that state, you can just ask that value function, and it's just one network call then, or one model call. But it has, of course, to be learned. And maybe last word here on this drawing, like here the return that you can see like on the bottom is just another word for the sum of rewards. And yeah, this is what outputs the value function, like the sum of rewards or like the return that you can expect. So why do we mention it yet? So because like in this quick overview of how reinforcement learnings are classified, this idea of a value function is critical, because you have like the policy-based methods, and they don't use this idea of a value function. They are in that sense very similar to the algorithms that you've seen in this course. So you didn't realize it, but most of these techniques that you've seen here could be like considered as policy-based reinforcement learning. You learn the controller or like what the agent does. And in contrast to that, what I'll be talking today are these value-based methods that use this idea of a value functions. Policies here are either derived implicitly, then it's really like a pure value function approach, or you can basically have like at the intersection of these two class of algorithms, like these actor-critic methods where you learn both a value function and a policy. Yeah, just to give you like a first overview of how reinforcement learning algorithms are classified. And yeah, let's now talk a bit more about these value functions. As promised like before, let's start with the Markov property. What is that? So in words, a system fulfills the Markov property if the future depends only on the present, not the past. Mathematically, it would look something like that here, that like if your environment transitions from one step to the next, the new state and the reward that you observe depend only on the last state and the last action. So again, maybe S stands for states, R for rewards, and A for actions. So examples of such Markov system could be, for instance, like a roulette game, where you can imagine like the outcome does not depend on what happened like the 10 games before. So in that sense, it's Markovian. Then you have like this little thingy. It's a physical system called the Ising system, and you have all these cells that can either be black or white. And in each step, like depending on neighboring cells, if there are more black ones, it's more likely to become black in the next step. And if there are more white ones, it's more likely to become white. And over time, it begins to form these clusters. It's like a well-known physical system that's used to describe phenomena like magnetism. And as you can also imagine, like as I said, like the transitions depend only on the last state. So in that sense, this would be also a Markovian system. The entire history is not relevant. And like physics in general is like in almost all cases like can be approximated as Markovian systems. Might be obvious for differential equations when you have only first order time derivatives. But also in the case of higher time derivatives, you probably know that you can always reformulate this as a first order system of higher dimension. So this Markov property should not really be considered restrictive at all. And yeah, it's needed in reinforcement learning because as I hope you remember, like you have these ansatz for the policy that it depends only on the last state. And if you like try to treat system that depends on the whole history, you would have like to modify that, and it would then be much more complicated. So let's continue thinking about what these Markov processes are. Let's take a look at that thing that is called a Markov decision process. And let's go through it. So we have states in the circle nodes, here denoted by S. In this case, we have two states, S0 and S1. Then we have actions in the rectangular nodes that follow after the states that you can choose. And after that, we have like on for instance, the purple arrow, we have a reward of 2. And this sort of like describes how a given reinforcement learning task is like set up. You have like, for instance, you can start like in state S0, then you can choose an action, for instance, like A0, and then you observe a reward like of 2. And then you are in state S1, and then there's another action, another reward, and then until the episode ends at the very right here. And yeah, so what can we do with that? Um, as soon as we fix a policy, that means as soon as we fix a rule like how to decide actions in a given state, we have a Markov reward process where the actions are gone and just the states and the rewards are left. And then we can also like choose to ignore the rewards and all that's left the states, and that would then be called a Markov process. And we can use these Markov processes now to explain better what these value functions are. So mathematically, a value function is a function that inputs like the current state, and then it outputs the expected future rewards, like the sum of the future rewards when you start from that given state. And there's also this pi symbol because like values depend on a policy. If you have like good actions, then you observe high rewards and your values are higher. Like if you have bad policy, then the rewards are lower and the values are lower. So yeah, it depends on the policy. And one thing that's critical about these value functions is they fulfill an equation that is called the Bellman equation. And it's actually quite easy. So in a deterministic case, like it basically just says the value of the current state is the value of the next state plus the reward observed in between. And yeah, I hope this makes sense to you. Yeah, as I said, like by definition, values are all the future rewards, and this just like split up in the next reward plus the sum of all rewards after that. So as I said, it's a consistency equation. When things are stochastic, then it's a little bit more complicated, but it's the same idea. So you have like, so what can be like sources of stochasticity? Either like the environment can be stochastic, or the policy can be stochastic, or both is stochastic. That's also possible, and yeah, the common case. And yeah, so, and the violation of this Bellman equation is often the starting point of many reinforcement learning algorithms that we will see in just a few minutes. So let me make it a little bit clearer now, like what these values are. Let's revisit this Markov decision process that you just saw. What would be the values for these two states? So as I said, like in order for this value definition to make sense, we first have to fix a policy. So let's fix a policy and say like in state S0, like we choose action 0. That means like we move along the top path in this problem. And then we can like compute the actions. For instance, like state S0. As I said, values are defined as the sum of future rewards, meaning we just follow the arrows. So for state S0, we have like a reward of 2 and then a reward of 1. So the sum is 3. That means the value of state S0 is 3. And for state 1, it's even easier because there's just one arrow to follow, a reward of 1. So the value of state S1 is 1. And just to explain like this idea of the Bellman equation again, like there's a second way to like compute the value of S0. Like we need not follow the arrows to the end, but we could just like use the value of the next state of state 1, that is 1, plus the reward in between, that is 2, and we sum it again, and we receive again like a value of 3 for state S0. So it's just two different ways of like arriving at the same result. And then we could also like ask ourselves what are the values for the second policy when we move like the lower path along the lower path. And then we have like for S1 it's the same, but for S0 now we have like a different situation. We have these two rewards, like 50% of the time we observe a reward of 0, 50% of the time a reward of 4, and like in expectation that's a reward of 2, so the value of S0 is 2. And yeah, what do reinforcement learning algorithms do now? Like they take a look at these values, see that policy 1 has higher values than policy 2, and then they decide for policy 1. So this is how reinforcement learning then basically works out. Like, of course, the problems are larger scale, but the basic idea is exactly that one. So yeah. There's one more thing I have to tell you about values. namely that there are two different types of values. And what you just saw are these v values. As I said, we fix a policy, and then we had like for policy 1, like S0 as a value of 3, the other one of 1. And there's now this thing called q values, and the only difference here is that as an additional argument for this value function, we use the actions. That's the expected future reward now, if you start in a given state and choose a given action in that state. And like for this problem, like the q values would be like the q value when starting from S0 and choosing action 0 would be like 3. So it's basically the same numbers as you've seen before. And yeah, there's 3 combinations of states and actions, so there's 3 q values. Yeah, and so let's get to reinforcement learning algorithms. What do we do if we had now like 2000 states and not just 2? And then we have to formalize it a bit more. And so value-based reinforcement learning algorithms are built up from 2 processes, value and policy iteration. So that's the first step, value iteration. We have like, so value iteration basically means finding the values. It's just a different word for it. And this is the definition of q values again. And we can now optimize for that by using 2 different losses. The first one is called the Monte Carlo loss. It's based on this idea of values as the sum of future rewards. What we do here is like we generate a complete episode starting from state S0 and action 0, and then we collect all the rewards that we that follow. And then we like compare like the prediction of the value against this observation, and yeah, this is basically a supervised approach. And in contrast to that, we have what is called temporal difference learning, or temporal difference loss. And it's based on the idea of values defined by the Bellman equation, this consistency equation. And what we do here is we generate not a complete episode, but only a transition from state and actions to the next. And we observe the reward. And yeah, the loss function here would be then basically like the violation of the Bellman equation. So this is Bellman residual that I hope you remember. But yeah, these are the 2 big classes of algorithms for value iteration. And now the second part, after we have the values, would be policy iteration. How to improve the policy. So as soon as we have the q values, we can just update the policy by doing that here. We basically take a look at the values for all the actions, and we choose that actions that gives you the highest values. And this over time will then improve the policy. And just again, like as quick summary, so these value-based reinforcement algorithms, they all iterate between this value estimation step and then policy improvement step. And over time, they will find good solution to reinforcement learning tasks. And maybe last word, so you might see that here this policy iteration step is almost trivial. So the hard part in reinforcement learning is always the value iteration step. And yeah, this is where the information processing over time takes place. Yeah, so how does a complete algorithm then look like? So this would be a Monte Carlo learning algorithm. So as I said, like the first thing what you have to do is like generate a complete episode. Then you initialize this g variable that stands for return, and you go through the episode backwards. So first you consider only the last reward and use it as a target to so you basically collect them in a list of all the returns that you get in the state and this action, and then you use that as a target to estimate the values for this state and this action. This is the value iteration step, and then next comes the policy iteration step, where you do this argmax of all the action, and you choose the actions with the highest value. And then you start over, like you go to the next element of like the for loop, like the second last reward. You use the sum as of the last reward and the second last reward then as a target for the value of the second last state. And you don't do that basically until you're done with the episode, and then you generate a new episode, and then you do this like for as long as you wish. And what would be like an example for temporal difference learning algorithm now? what we do here, like as I mentioned before, like we generate now transitions, not complete episodes. Then we compute the violation of the Bellman equation, the consistency equation that values have to fulfill. Then we update the values by using like this violation with a step size parameter or learning rate, and then we update the policy again. And yeah, that's basically it. So and yeah, this specific variant of temporal difference learning here is called Q-learning. Yeah, it's a rather well-known algorithm. And a little visualization now of what like the result of such algorithms look like. So there's a reinforcement learning task that's called grid world. What you can do here is basically you can move on all the fields like one step, and you start in the bottom left, and on the top right you get a reward of +1, and on the middle right field you get a reward of -1. And now, yeah, your goal is basically to maximize reward, like find your way to the top right field. If you train Q values on that, it would look something like that. So as I said, like Q values are a function of states and actions. The states are the fields here, and the actions are like the 4 directions on each of these fields that you can go. And yeah, if like the thing is halfway decently trained, then you can just follow the big numbers, and then you will arrive at the like best goal field. So the green gives you a reward of +1. And yeah, so far so good. So a few words on neural networks and how they come into play here in reinforcement learning. So function approximation is needed if either the number of the states or the actions are too large or even continuous, or like both at the same time, like states too large and actions too large. Then you approximate, for instance, like the value function by a neural network. That means now it depends on parameters theta. And what you can do now is like all these algorithms that I've shown you basically give you a rule for how to update the values. You just use backpropagation to like translate this value update into a parameter update, and then you can train neural networks with these algorithms. So there's not much to it actually. And as a last example for like reinforcement learning algorithms, this is DDPG. It stands for Deep Deterministic Policy Gradient. It's also quite a famous one. It's an actor-critic method. Remember, that means it does have a value function and does approximate policy at the same time. So there's more than one neural network involved here. And actually there's quite more happening here. So the idea is kind of sort of just to like roughly understand it, because there are some things you're not familiar with. But if you take a look in the inner loop, you might be able to tell like at the very beginning there's something like data generation happening, like before like sampling transitions. That's the same thing happening here. So you might get already like hunch that this is more like temporal difference learning, which requires transitions, not complete episodes. Then there's this thing called a replay buffer. We're not familiar with that. But after that comes something you might recognize. So there's this value iteration step again, and that looks like very similar to the temporal difference equation that I just showed you a couple of slides ago. So yeah, it's basically like stretched over 2 lines. But it's this consistency equation that you use as a target loss. And yeah, this is the value iteration step, and afterwards comes the policy iteration step. Actions are continuous now, so you don't have like this argmax function over discrete actions, but you have now gradient over actions. But I hope you can recognize that this is like policy iteration, like what's happening here. And yeah, at the end there's something else we don't know about. There's these target networks. But yeah, that's basically how you can try to understand like even more complicated algorithms by looking out for these value iteration and policy iteration steps. And yeah, so far for the first part of the lecture. So we'll be having a break of like 10 minutes now, and then I'll continue the second part. Thanks. Okay, let's continue. We want to understand now in more detail what motivates some of the ideas that are presented in the first half of the lecture. So one way to look at these ideas in a logical order is the following. So we have different components of a learning system. For each of them, you have a choice of using either a familiar one-step method or like a reinforcement learning multi-step method. Remember, reinforcement learning tasks are multi-step tasks. And so what are the components? We have a model. We have the model where you have the choice between autoregressive models or value functions. We have, for the loss, we have like the supervised methods like Monte Carlo learning or residual-based methods like temporal difference learning. And for the optimizer, we have gradient methods or non-gradient methods. And so for each of that component, we will now give an argumentation of why a change from one-step techniques to multi-step methods is necessary. And what is important is that stochasticity is like a key property to motivate these changes. So if you're considering a deterministic task, then it might very well be possible that you can get perfectly away with just using one-step methods. And yeah, also in the second part now, there's plenty of connections to physics now, which I hope to make clear. So let's start with autoregressive models versus value functions. What are the differences? So autoregressive models, I believe, have been extensively covered in this course. Let me remind you nevertheless of their functional form. So what we do in autoregression is we train a model and input the last state of the system, and we get as output the new state of the system. And what that practically means, what we do is like we perfect a model on one-step predictions, and then we apply it recursively to receive a multi-step prediction. And in contrast to that, we have like value functions, which are sort of a computational shortcut. You have only one call of this model, and you directly get as an output the sum of all future rewards, so a multi-step prediction. So in that sense, this is like a true multi-step method. And one could also ask oneself now, like, what is a multi-step predictor for the case of a physical system? Like when you have a differential equation and want to learn the solution. Most of the course, I believe, was about this sort of task. So how could you do that? Like you could discretize it on a grid, like at specific points in time. And like the one-step approach, again, would be like autoregression. Like you train a model that inputs like the last field values, and you get as an output the new ones. And multi-step approach would be like to directly parameterize the solution, that you train a model that depends on the time you're interested in, on the time step you're interested in, and you output directly like the field configuration at that point in time. So again, like autoregression needs n calls for n-step prediction, and this multi-step approach is just one network call. And you might also like recognize like the similarity to physics-informed neural networks, which basically do the same thing as this multi-step ansatz here. So what are, like as mentioned, autoregressive models are one-step predictors. Applying them to multi-step tasks can cause problems. And among others, like as I mentioned, like for n-step prediction, you require n model calls. Another thing to have in mind is that you learn an entire state trajectory. So even though you're not only interested like in a prediction after 50 steps, you have to learn all the 49 states of the simulation or of the system in between. And in stochastic settings, that is even worse, where you don't just have like this one trajectory, but you have a distribution of trajectories. You have to understand them all in order like to make a prediction after after n steps. So that way the learning task is much more complicated. And I'm sure you also know that here these autoregressive models suffer from exponential error growth over time. This is because, you know, you can always just train a model like approximately. There's always some imperfection, some deviation that remains. And this can amplify over time until it becomes like relevant if you wait long enough, and can also like degrade the quality of learning system. Yeah, so to illustrate these disadvantages, let's look again at the easing example. Let's say our goal is to learn to predict who wins, and this basically means like if the thing is going to be white or mostly black in the end. So what would autoregressive models do here? As I said, they would learn the complete environment dynamics. So basically how one transition, basically all sort of like transitions or stays from one to the next. And this is especially critical here because what's kind of extreme in that example is that every element of the state space, like every state that you could possibly have, can be transitioned into from any other given state. So this is really like the branching factor, so to say, in this problem is really like as large as it can get. And in contrast to that, like you could have like a value function, and what it does, it can learn possible shortcuts. For instance, like it could, like if at some point in time here you have 3 times as many white cells as black cells, then it's like almost certain that white is going to make it in the end. Or another feature that could be like learned by such value function is like it could look out for clusters. Like if there's some big clusters of white or black cells, then this makes winning all the more likely. So yeah, as an illustration again. Another one would be like card pole prediction. So card pole is this little thingy here where you have like a card and a pendulum attached to it, and you can only like apply force to the card, and the goal is to swing up this pendulum. But we're not interested in the control task here, but only like in prediction. So we have like some initial states and some forces we apply, and we want to know where the card is after, let's say, 50 steps. And we can train like a bunch of different methods here. So what you see here are like 3 autoregressive models and 1 value-like ansatz. And in the middle you see like some learning curves that go down. That's basically all you can see here, because like the losses are different, so the curves here are not really comparable. But on the right you can see that the error curves, like when you predict over time, that they look very different. Like you have the autoregressive curves that basically all increase from step to step to step. And you can see that these value-based ansatz, like the purple one, in the first 50 steps where it was trained on, like the error is mostly constant. After that, it also starts to increase. But yeah, the characteristic error growth is different in these 2 types of methods. And another thing that I mentioned before, like if we compare here some data of the training setup, especially the last row where the prediction time is written down for each of the models, you can see again like the autoregressive models take much more time for predicting. This is because again they have like to evaluate for 50-step predictions, they have to evaluate the model 50 times. And in contrast again, like the value function, just this one network call. Yeah, so this was about the model. Now about loss functions. Can we just use supervised methods in reinforcement learning? Let me remind you of what the update equations for both losses look like. So we had the supervised learning methods like Monte Carlo for value estimation, where we have like the model prediction V compared against actual observations of rewards. And in a physical context, this would correspond like, there's also like these supervised methods that go sometimes by the name trajectory learning. Like if you want to learn a fluid simulation, you can use an initial state and use a numerical method like to evolve it over time, then you have a fluid simulation over time. And if you want to train a model to predict that, you can just like compare every prediction of the model against like the fluid frame at a given time. So you can train a model to generate a fluid simulation. These are all supervised methods because you have always like prediction against observation. And in contrast to that, you have like the residual-based methods where, for instance, like in temporal difference learning for value estimation, you do that with the Bellman equation. Again, that's the consistency equations values have to fulfill in order to make sense. What's special about that is that here in the loss, or in the next step then in the update equation, you have the predictions appearing twice. So this is then not supervised learning anymore, where you just have one prediction and observations. Here you have two predictions and possibly observations. And this is also similar to physics-informed training, where you have like an equation as a loss, or as a loss function. And there also like the state predictions appear more than once in loss functions. And when we want to understand now how do these methods differ, we can look at this little example here. This gives a first idea of how Monte Carlo learning and temporal difference learning are different. And because of the analogy, this also like explains or gives an idea of how supervised learning is different from physics-informed training for physical systems. So I ask you, like, how would you estimate the values in this Markov reward process based on the observed episodes? This is the Markov reward process, and these are the episodes. And so how to read that? For episode 1, we start in state A, then we move to state C while observing a reward of 0, and then we have a reward of -1 on the last arrow, and the episode ends. And for episode 2, we start in state B, have a reward of 0, or then in state C, and then a reward of +1. And yeah, there's several acceptable answers, and maybe it's easiest to start with state C, the values of state C. So give you a couple of seconds to think about that. So these were the episodes, and let's look first like at the Monte Carlo answer that you get for this question. So as mentioned, state C is easiest. We have two observations of what happens from state C on. Like once we had a reward of -1 and once of once of +1. And that means like in average we received a reward of 0, so the value of state C is 0. And now the way Monte Carlo estimates the value of state A is like we have one data point basically where we have been in state A, and then we follow the rewards that we observed from that state. Like we first observed a reward of 0 and then a reward of -1, means the value of the state is -1. And just the same thing for state B. So we had one observation of state B, then we had a reward of 0 and a reward of +1 there. Sum is +1, so the value of state B is +1. And in contrast to that, what temporal difference learning does is, so the value of state C is just the same because it's a final state. For final states, these two methods do not differ. For state A and state B, it's different. So, as we talked about earlier, the temporal difference learning is based on the Bellman equation. So we compute the value of state A there as the value of the next state plus the reward in between. So the value of the next state of state A is the value of state C, that is 0, and the reward in between was 0. So here the value is 0. And same thing for state B. Here in temporal difference learning, again, we compute it as the value of the next state, which is 0, plus the reward in between, which is 0. So the value of state B would be 0. So Monte Carlo and temporal difference learning give two different answers to this question of estimating the values. And one way to think about that is like that what Monte Carlo is trying to do minimizes the error on past data, or like on the training set. And in contrast to that, like temporal difference learning minimizes the error on future data. And it does that basically by taking advantage of the Markov property. So we're staying on that topic. So this is another example of how temporal difference learning and Monte Carlo differ from each other. So the task here is to select the website design that leads to the largest sale rate. And we have 3 different web pages. And what a customer can do when he's on one of these web pages, he can either proceed to the checkout site or he can leave. And on the checkout site again, he can either proceed or decide not to buy the product. And this also is like a multi-stage process, like the website stage and the checkout stage. And one can now ask the question which one of these web pages would you choose to advertise the product, based on this data. And similar as before, there's 2 different answers to this problem, depending on whether you want to do Monte Carlo or temporal difference learning. And yeah, so I'll leave it as sort of a home exercise if you're interested. So the 2 estimation procedures now, Monte Carlo and temporal difference learning, they can of course be mathematically analyzed. And you may know from your statistics courses that in order to determine if one estimator is better than another estimator, what you have to do is compute their variances and compare them. And so how does this look like? So for the final state A here in this Markov decision process, if you want to estimate the values, the 2 estimates, as we already know, are the same, so they give the same results, and as a consequence also the variances of the 2 estimators are absolutely the same. But we can just look at this expression just to understand it. So the ability to estimate quickly the values, on what do they depend? Here on the reward process after state A, obviously if the rewards are noisier, then it's harder to estimate the values. And also the number of episodes, the number of times you've observed rewards after state A. So you have these P, N, and M episodes starting in the states E, D, and C. And the more of them you have, the better you can estimate the value of A. But here it's still not interesting because the 2 estimators are the same. If you estimate now the values of B, this is where the 2 estimators differ. And what you can see here again is also similar to the previous examples, just in a more mathematical formalized form, is that the expressions for the expression for the estimator for temporal difference learning here, that the denominator is larger, meaning the variance of this estimator is smaller, and so it's easier to estimate this value with temporal difference learning. And you can now continue this idea to state C, where the difference gets even bigger between the 2 estimators, because the Monte Carlo estimate can just use the M episodes that start in that very state, and the temporal difference learning estimator can also use the episodes from the other states, partly at least. And yeah, the bottom line here is the TD estimators have lower variance, and also what's useful to keep in mind that this kind of structure of this Markov reward process is of course part of larger Markov reward processes. And I hope you can see the trend here that the difference of this temporal difference learning Markov Monte Carlo estimators, it gets bigger the longer this Markov chains get. And also in the case of that you have only a final reward, then these expressions differ the most. This is exactly corresponds to the toughest reinforcement learning task, where you have long sequences and only one final reward, only one information, so to say, to get an idea of what actions are good and what aren't. So sort of a mathematical justification here. And yeah, so and another last example on temporal difference learning in Monte Carlo. So this example is called Going Home, and it illustrates a bit how temporal difference learning in Monte Carlo can differ on just one episode, and how you can use temporal difference learning also not only to estimate values but also other quantities. So what you have here is like a model that somehow predicts like how long does it take for you to get home. And you have these different stations here, like the university substation, subway station, home subway station, and then home. And then you have these observations, like how long the different steps actually took. And we want to process this information now. So these observations sort of correspond to what earlier the rewards were. And yeah, let's go through it. So we are at the university and our model says like there's 40 minutes left, and then we walk to the subway station and the model says there's 35 minutes left. And our observation is it took us exactly 5 minutes. So how does Monte Carlo process this information? At the moment, Monte Carlo does nothing because remember, Monte Carlo requires complete episodes. So it cannot do anything yet. But in contrast, temporal difference learning, like it can work with transitions, and it basically checks for consistency. So like the predicted difference were 5 minutes, and this is also the observation, so this is consistent. So temporal difference learning does nothing here. Then in the next step, like when you take the subway ride, the model basically predicts it takes 35 minus 5 minutes, so 30 minutes. And what it actually took were 25 minutes. So in order to make that more consistent, temporal difference learning would decrease the university subway station prediction. And then if we go to the last part of the of going home, we have like the home subway station where predicted is 5 minutes left, and here it takes us unfortunately 15 minutes. So in order to make it consistent, temporal difference learning would try to increase the home subway station prediction. And now the episode has finished, so also Monte Carlo can start doing something. So for the final state, as I said before, like temporal difference learning and Monte Carlo learning do the same. So Monte Carlo would also try to increase that estimate from 5 minutes to something more. And then if we go further back, like to university subway station, the prediction was 35 minutes. What Monte Carlo now does is add up this 50 minutes and this 25 minutes to like see that it took 40 minutes to get home from university subway station. So it would increase that prediction. And same thing like for the last state, for like being at university, where the prediction was 40 minutes, but it took in total 45 minutes, so Monte Carlo would also increase that prediction. Yeah. So much about the difference between temporal difference learning, Monte Carlo, and the losses. And the last topic for today is how to optimize multi-step setups. Basically, after we have specified a model and a loss, what to do with that. And as before, there are reasons not to use the familiar one-step methods like gradient descent for multi-step tasks. So some introductory statements on that. So what do I mean by non-gradient? So that's the classical methods like for optimization, like Newton's method, gradient descent, momentum. And I mean something completely different here. So we are interested in something that is first order, because as you might know from other deep learning courses, like 0 and second order optimizers are like have scaling issues for large models. Then we obviously not gradient descent. And also we are not interested in gradient-based methods that, for instance, like momentum could be considered to be a gradient-based method because, you know, it computes the gradient and then sort of post-processes the update to make it better. And so a complete specification of what we're interested here could be like, if you don't mind lengthy expressions, a first order non-gradient based method. And what does such a non-gradient method update look like in practice? So that's good news. So you've already seen it earlier. Remember the temporal difference learning loss. So the update that we used here was that one. And it's a non-gradient method or non-gradient update. And how can you see that? So remember that like in this residual losses, you have two predictions, like like here for this specific one, like two variables, like the earlier value and the later value. But we choose only to update one of them. Like in true gradient descent, we would obviously compute the derivatives like for both of these values and apply updates there. So in that way, you can already suspect like that we did earlier was not a gradient update. And how can this be motivated, like to leave off one of the terms of the gradient update? In temporal problems, there's a natural direction in which information flows. So if you take a look again here at this little Markov chain, like rewards on the edges and always 1, the corresponding values like 5, 4, 3, 2, 1. And let's say we have a new observation now, like somewhere in the middle, a reward of 5. Then this presents like an inconsistency in this chain, and the question is how to resolve it. And what happens in value prediction is that the information flows to the left. Like the predictions on the right are not affected by early observation of rewards because value functions or values are defined on future rewards. So for values, information flows backward in time. But second example here, like a physics example, let's say we have like one particle in a force field, like x dot dot equals f. I think everybody's seen that at some point. Let's say we want to like evolve that system with an Euler step, say let f and dt is 1 to make the expressions simple. Then we have like these evolution equations here. And let's say we have a model that we want to train to learn this system, and it has learned these values. Then if you compare like the predictions from step to step, you can see also there's like this one transition where they don't fulfill the update equations. So there's an inconsistency here. And what's different here in this initial value problem, like that information flows forward in time, whereas like in value prediction it flows backward in time. But in both cases there's like a specific direction, a natural direction in which information flows, and the non-gradient update basically takes care of that observation and like propagates information only through either the earlier or the later prediction. And one practical consequence of propagating information in a temporally consistent way is that the conversions to solutions is faster. So that's probably not surprising, but also beyond that intuitive arguments that I just gave you, it's well established. So one way like to measure it is like we can take just any Markov reward process, there's nothing specific about that one, and estimate the values, and then we can like record like the convergence rate, like how fast are the values approached. And what you can see here is like the blue curve, that is the gradient method, has like a consistently higher convergence rate than the non-gradient method that is the purple data points here. So maybe as an explanation, what is the convergence rate? It's the factor by which a loss decreases or increases in each step. So if a convergence rate is larger than 1, that means like the loss increases, so it diverges. And if it's smaller than 1, like the loss decreases, so it converges, and the smaller it gets, like the faster it converges. So in that way, like the purple curve is like consistently better. It's independent of the learning rate. And yeah, so maybe a short comment also, like residual gradient is another name for like the combination of temporal difference loss with a gradient method. And temporal difference is also unfortunately often just used to describe this combination of temporal difference learning with a non-gradient method. It's a bit unfortunate in the literature, but that's the way it has established itself. Just so you've heard it once at least. So for the other differences between like these gradient and non-gradient updates for temporal difference learning, we need function approximation. So the convergence rate discussion that we just had did not require it. So as before, for the values in this loss, now we introduce again parameters theta, and we can write down now the gradient update again, like we just have to apply the chain rule. It looks like that. And again, we get the non-gradient update by just neglecting one of these two terms. Like for values, we don't want to propagate through later predictions, so we just forget about that term. So we get like the gradient and non-gradient update, like for the case of function approximation. And now the question is like, do these non-gradient methods always converge? So the slide is about convergence itself, not the rate of convergence. And you probably know that gradient methods have a built-in convergence guarantee through the steepest descent property. And that's something that is different here. So there are known examples where these non-gradient methods do basically nonsense, meaning they diverge. And this is one of them. So this is sort of minimal. There are just two states and one parameter, w. And the way it is parameterized, you can see like in the figure, like the first value is parameterized as w and the second value as 2w. And it's a Markov zero reward process. That means all rewards are zero. Then you can immediately tell that all the values in the problem have to be zero. Like this is the solution we're trying to approximate, and we just see like, can these non-gradient updates find them? And if you do the math, then you can then leads to this update equation on w that you can see here. And yeah, unfortunately, like it's an exponentially increasing function, so it does not converge to zero. It's not a sign error or something, so but it's really the true update. And this is sort of a problem. So on the other hand, like next to these known examples of divergence, there are also some convergence theorems. We're not going into details, but what they usually depend on is linear function approximation and on policy sampling. So on policy sampling means you have to show like the transitions according to the natural frequency. What it means is like, or like in comparison for gradient descent, you don't have to do that. Like if you're classifying cats or dogs, and there's this one cat that you like especially, you can just show it 100 times to the network. It might converge to another solution, but it still converges. You cannot do that for this non-gradient methods. You have to show the transitions according to the natural frequency of the Markov process. And beyond that, it's sort of an open problem when these methods converge and when they don't. And yeah, so things get more complicated as soon as nonlinear function approximation comes into play. And yeah, I said it's open research at the moment. And the last difference, like besides convergence and convergence rate, are the fixed points of these two methods. So what's happening in practice is that they find two different solutions depending on whether you use gradients or such a non-gradient method for optimization. And just to make this plausible, so you have like this linear, let's say we do linear function approximation with value estimation, then we have like a linear sort of problem. In this forward matrix F, like somehow is encoded like the function approximator and all these temporal differences. So like the precise form is not really important, but in the end it's a linear problem as long as you do linear function approximation. If you now compute like the gradient update just by applying chain rule, I'm sure you know that it would look like that here. And if you ask yourself now, where does this like end this update procedure? What is the fixed point? You just have to like set this gradient update equation to 0, and then you get an expression for the theta. At that point, you don't perform any updates anymore because everything's 0 there. And in contrast, if you apply a non-gradient method, that corresponds to a modified backpropagation path, because you decided not to backpropagate feedback through certain predictions. And as a logic consequence, like you find a different fixed point because there are now different matrices occurring in this fixed point equation. And yeah, just to make it a bit plausible. So important lesson here is it's two different fixed points these two methods find. And this is now crucial, like to understand why you cannot use gradients for temporal difference learning. And the argument goes as follows. So even though we don't use it for training, our goal is still to minimize the supervised loss. We are still interested in finding the true values of a given problem. We use the residual loss for training only because of its statistical benefits. We talked about this like in the last section, like we talked about the difference between Monte Carlo and temporal difference learning, and then one estimator has better statistical properties. And classical optimization methods, what they do is find the minimum of the loss that they are applied to. So that's why it's completely fine to use them for supervised learning, because here the loss that you're interested in and the loss that you compute updates on are one and the same. But for residual objectives, like we are not interested in finding the minimum of the residual objective. we are interested still in the supervised loss, and this is why we need a non-gradient method in order not to like find a point we're not interested in. So this might seem a bit abstract, but here's a final example, like to which I hope will give you like a rough idea of what is happening here. So this is like a harmonic oscillator problem, like prediction of a physical system. And we do physics-informed training because that's one form of residual training. And we have like these two losses, like here in figure part A, like the physics-informed loss. This is the loss we compute updates on, but we're not really interested like how well like the solution looks in that loss. Then we have the supervised loss. This is the one we are interested in. Then the third plot we can ignore for the moment. And the last plot on the right here is the phase space or physical space. So the harmonic oscillator is basically a system that moves on circles in this phase space. And we see here like 3/4 of a circle. Here this gray curve that depicts the solution. And what we now do is like we optimize this model and loss with either gradient method or non-gradient method. And we have also Newton here that sort of does the same thing, finds the same solution as the gradient method, because these are all classical methods. And it's like a quadratic problem. So what you see here with Newton, like where the curve is, this is already the final solution, because in quadratic problems, like Newton just needs one iteration step. And you can already see that it does not find like the actual solution, but something different here. And I hope the video works. So if you optimize it now, you can see these two different behaviors of the gradient method and the non-gradient methods. So the non-gradient method, like the blue curve, you can see like it approximates the solution and quite quickly. And you can see that the gradient method also finds this different fixed point, like the same that Newton does. And this is the minimum of the residual loss that these classical methods find. You can also see that in the first plot, like the loss is minimal for these two methods. But we are interested in like the supervised loss, like the distance to the true solution. And this is what the non-gradient method approximates well better. And yeah, so this is a summary again. So how to understand the differences between these two types of methods. So in terms of convergence, so this is a case where this non-gradient method obviously converges. You can see it. So then the second thing is like the fixed points that are different. You can see this also in the right plot, that they approach two different solutions. And the last thing is the convergence rate. I mean, you can see it in the right plot that the blue curve way faster like finds the solution, but also in the third plot. So this is the best way to measure like the distance to the respective like to the two different fixed points that they approach. You can see that like after, I don't know, 30 steps or something, it's done. Or no, it's actually 100 or something. But it's way faster than like the gradient method. Yeah, so quick summary for the lecture today. So reinforcement learning explores an alternative approach for multi-step tasks. We've talked about these value functions, temporal difference learning, and non-gradient methods. And there are some analogies with physical learning techniques, like for instance physics-informed training, and like it addresses like computational, statistical, and optimization bottlenecks of various sorts that you have in multi-step problems, and this ultimately justifies them. If you're interested to look deeper, like here are some references that I can recommend. And yeah, I think this is done for today. So thanks for coming and enjoy the evening. Thank you.